Hey y'all, so here we are doing 10.3. Um, Again, in our book, it's not really chapter 10.3, but we're just calling that to keep organized in some way. What we're learning is how to integrate parametric polar and vector curves. Basically, how do we find the area under the curve, the area bounded by these curves, how do we find an arc length for these curves, and then we'll be able to find the area of a surface as well. So most of them are going to boil down to knowing some formulas. At some point, you learn how to derive these formulas. Uh, so my suggestion for now is write them down, maybe put them on a note card. It's just kind of like learning the area of the solids of revolution. You have to know how to get there, right? So the area under a parametric curve is going to be given by this. The integral from a to b, where a is the t value and b is a t value of g of t times f prime of t, where the g of t is the y, right, and the f of t is the x. And so what we have down here is f prime of t, which is the derivative of the x piece. And so let's look at an example and see if we can figure out how this goes. So this example says, find the area bounded by x equals 2 sine t, y equals 3 sine squared t. Basically, we can set up an integral. We can say the area is going to equal g of t, which is the y piece, right? So we're putting the y piece here, times the derivative of the x piece, right? So we need to find dx dt. Let's go ahead and do this. Dx dt equals 2 cosine t. So we're going to put 2 cosine t here, and we're integrating with respect to t. What we're missing and what it gets a little bit confusing here are what are the limits of integration, right? We need to figure out where are we integrating from, because they didn't give us like from t equals 5 to t equals 7, right? They're just saying integrate the region that's bounded by it, right? Meaning like this should be somehow shown to us. So what I'd like to do is go ahead and graph this on a calculator, and then the calculator will help us see how to do this. Okay, so the first thing we're going to do on our calculator is we're going to change the mode. So go to mode, and notice that if you go down, you can actually change your calculator into parametric mode, right? And then we can go and we can graph this. We're just going to graph the original function, which is 2 sine t, and the y of t is 3 sine squared t, so it's going to be sine t all squared. If you're worried about whether that's squaring the t or the whole thing, you can insert a parenthesis here. Oops. 3 sine t squared, right? And then we can graph this, and I'm in a different viewing window. Look, and it's going to look like this, which we can change this a little bit. I don't need to see so many x values. Let's change this from -5 to 5. Right, so it looks like this. Let's see if we can zoom in on it even more. No, that's what we do. We need to do negative. No, we don't need to go that far in the negative direction because there's not that much negative in there. All right, so that's what it looks like. Basically what we're doing is we're finding the area under this curve, right? So just like we did before, we're just going to find the area beneath this curve. And so what we need to know is like, well, how far, where do I integrate from? What's the t value right here on the left hand side? What's the t value over here on the right hand side? And that's what our limits of integration are going to be. Okay, so how do we figure out how far right this thing goes? Like why does it stop going to the right at x equals 2, right? You can kind of see on this graph that it's stopping at x equals 2. Why does it stop going to the right at x equals 2 and then start coming down, right? Like if you trace what happens to this function, right? Like you would start at 0, right? And you'd go this direction, and then it basically bounces back and goes this direction, and then it bounces back and goes this direction again, right? And then it's going to stop at 6 just because that's the window I set was for t to stop at 6. But why does it turn around up here, right? So let's try to figure out what that t value is up there, right? So go all the way high up as you can. Notice it's like 1.570. Does that look familiar to you as like what that number is? Does it look like half of some special number we know? Turns out it's pi over 2, right? And if you go to this leftmost point over here, it's going to be negative pi over 2. So why is it pi over 2, right? Like remember that the x coordinate is being defined by x equals 2 sine t, right? So like what's the farthest right x can be, right? Like imagine there's this x equals sine t. What's the biggest sine t can ever be? 1, right? Like sine of pi over 2 is 1. But this 2 in front makes it so that the biggest it can be is 2. Once it gets to 2, it starts decreasing again, and the smallest it can be is negative 2 in this case, right? So, and when does it reach negative 2? Well, it reaches it at 3 pi over 2, but in this case it's easier just to say negative pi over 2, which is the same the same basic coordinate. So this is basically going from negative pi over 2 to pi over 2. Right, again, because that's the maximum the x value you can get. It's the farthest right it can get is at t equals pi over 2, and the farthest left it can get is at t equals negative pi over 2, or 3/2 pi. And I think we could, let's check this, but I think you could actually go from pi over 2 to 3 pi over 2, and you should get the same answer. And we'll check that in a second. So now what we need to do is we need to integrate this, right? So we're gonna, we can go back to our calculator here, do math 9. We're gonna integrate negative pi over 2 to pi over 2 of 3 sine t squared. That is going to square the whole thing, times 2, let's make it clear, times 2 cosine t, close all the parentheses appropriately, I think that's where we need to be, dt, and when we do this, we're going to get an answer of 4. So the area beneath this curve is 4. Just out of curiosity, let's see if we could have gone from positive pi over 2 to 3 pi over 2. I don't see why it wouldn't work. But you never know. Oh, it gives us negative 4. Oh, because that would be going, I guess, backwards or something like that. So it kind of works, but we get a negative answer out of it. So that's the answer there. Maybe since that was kind of short, let's do another example, right? Let's do that's similar to this. Let's say x is defined as 6 times theta minus sine theta, and let's say y is defined as 6 times 1 minus cosine theta, right? Parametric has a parameter. It doesn't always have to be t. It could be theta, and we're gonna restrict ourselves to go from 0 to 2 pi. So like we're given the limits here, right? So basically it's the same idea except with thetas. So I need the y piece just as it's written, right? We're using that formula. So we're gonna say the area is equal to the integral In this case, it's going to be 0 to 2 pi, so that's nice that we don't have to figure out that weird stuff. We're going to put the y piece, which is 6 minus 6 times theta minus sine theta, and then we're going to put the x piece, the derivative of the x piece. Oh, sorry, I wrote the x piece here. I need to erase. Let's see. Let's stretch this out so I actually have the eraser available. We're doing the y piece goes here, right? So 6 times 1 minus cosine theta, and then we're going to multiply by the derivative of the x piece, which the derivative of that is, and I'm sorry, this should be a 1, not a theta. That's a 1. The derivative of that is simply, no, it is supposed to be, oh my, I'm sorry, this is a theta. I'm looking at the problem over here, and it is a theta. Derivative of that is simply 6 times 1 minus cosine theta. Right? This is going to be 6 times 1 minus cosine theta. Right? If you take the derivative, that's what you get. So we can go ahead and simplify this a little bit. If we're going to try to integrate it, 0 to 2 pi, it's going to be 36 times 1 minus cosine theta quantity squared. And we can get back out our calculator, and in this case we might not want to plug in a theta, but it should still work, like I said last time, and it didn't quite work out. But let's do this from 0 to 2 pi, and then we're going to do 36 times 1 minus cosine, it's t instead of theta, but like I said, I believe it'll work. This piece is squared. If anything, we could change it to something else, and we're going to get 339, which the answer is 108 pi. So let's just check if these are the same. Yeah, so it gives us, like if you did it out by hand, you'd get 108 pi. Right, that's the area of that one. Okay, so next we want to talk about arc length, right? Arc length is basically if you have a function like this, the arc length is like if you had to walk along this curve, how far would you walk, right? It's like the distance of a windy road, right? Imagine you have some weird windy road, you want to know like how long is that road? Well, this is what you would do to find it. So basically, again, it's the integral from a to b, where these are like t values, right? Those are t values. We have to, it's basically like distance formula, right? We have to take the square root of the derivative of the x piece squared plus the derivative of the y piece squared. So let's check out an example. Let's see. Okay, so let's start, since we need the derivative of x with respect to t and the derivative of y with respect to t, let's go ahead and find those right off the bat. Right, dx dt is the derivative of this, which is going to require product rule. It's going to be e to the t cosine t plus, actually it's going to be minus, but minus sine t e to the t. And then dy dt is going to be something pretty similar. It's going to be e to the t sine t plus cosine t times e to the t. And the arc length, we're going to say L is going to equal the integral from 0 to 4, right? They gave that to us. They said from 0 to 4, that's nice, of the square root of dx dt squared, which is, oh my, sorry, I don't know what just happened. Okay, I just pressed on one of these tab things as I was drawing. So it's going to be the dx piece, which is e to the t cosine t minus sine t e to the t, that whole thing squared, and then plus the y piece squared, so plus e to the t sine t plus cosine t e to the t, all squared, right? The square root goes over the whole thing. We're integrating with respect to t. So, like, you know, if you had to do this by hand, it'd be a pain in the butt. If you do it with a calculator, it's pretty straightforward. But if you have to do it by hand, just know that this one's not particularly nice. Although I do think I see a way to do it where it's not too bad. So let's notice that there's an e to the t inside these parentheses here, right? So we're gonna like factor out e to the t times cosine t minus sine t squared, right? There's still a square root over this whole thing. And then the same thing over here where there's a e to the t times sine t plus cosine t, the whole thing squared. Let me make sure I put the squared on the right spot. No, we need an extra parenthesis, right? Because the square goes to e to t as well. And then basically this can turn into e to the t squared times cosine t minus sine t squared. Same idea over here, right? It's going to be e to the t squared times sine t plus cosine t squared. And so, again, we could factor out the e to the t squared since they both have it, right? There's going to be e to the t squared times this whole thing, which if you multiply this out, you're going to get cosine squared t, right? So I'm gonna multiply this out, right? I'm using FOIL. Cosine t squared minus 2 sine t cosine t plus, this is gonna be plus sine squared t. I'm gonna multiply this one out as well, which is gonna be sine squared t plus 2 sine cosine t plus cosine squared t. And at this point, you can cancel some things out. Notice that this will cancel this. And then we have 2 positive cosines and 2 positive sine squareds. So this whole thing is going to simplify into, this thing should have been like the cosine in parentheses there. So this whole thing is going to simplify to e to the t squared is the same as e to the 2t, right? They're using that property, times there's 2 cosine squared t's and there's 2 sine squared t's, right? And then you can factor out the 2. So it's going to be 0 to 4, 2 e to the 2t, and you're left with cosine squared t plus sine squared t. And then that cosine squared plus sine squared just turns into 1. So we're left with 0 to 4 of 2 e to the 2t. And there's, this whole time, I haven't been writing it, but this whole time there's been a square root over this whole thing, right? I just wasn't writing it because it's tedious to write it. And so we can simplify that into square root of 2 on the outside, right? Take the square root of 2. And then we have e to the 2t. The square root could be written as a fractional exponent, which would then simplify to e to the t, which after all that mess, it turns into e to the t, which is kind of funny. Integrate e to the t, you get e to the t, so this is root 2 square root of 2 e to the t, evaluated from 0 to 4. So it'll be square root of 2 times e to the 4th minus the square root of 2 times e to the 0, which is that. So we get this as an exact answer. If we did it in our calculator, we'd get the approximate answer, but it'd be something close to that. All right, so I encourage you to try to go through all those algebraic steps yourself and understand each one, because that's what it looks like if you had to do this without a calculator. That's what you do. All right, let's move on to area of a surface generated by revolving the x-axis of the arc defined by x equals 3t minus 3 minus 2t and y equals 20 minus t squared, square root, from 0 to 4. So the idea is we're going to find a volume of revolution of the area. It's basically the same thing we were doing before, right? Like you have some area formed, and we take that area, we revolve it around the axis, and it makes a volume. The same idea is going on here, except where the curve is defined parametrically. You can see the formulas up here. Again, these are like t values, right? So it's just going to be s equals the integral. They gave us the intervals, which is 0 to 4, of 2 pi times y, which y is the function that is here, which is the square root of 20 minus t squared. That's what y is, and we're going to multiply that by the square root of the derivative of the x piece plus the derivative of the y piece with respect to t. Right, so I need to figure out what's the derivative of the x piece, what's the derivative of the y piece. Let's do that. Where should we do that? Let's do that. Maybe we can do it just on the side over here somewhere. So y is 20 minus t squared, square root, which is that to the 1/2 power. So y prime is going to be 1/2 20 minus t squared to the negative 1/2 power times the derivative of the inside is negative 2t, and so the derivative is going to be it's going to be negative t, 1/2 cancels with the 2, over the square root of 20 minus t squared. The derivative of the x piece is a lot simpler. Dx dt is simply negative 2. So this piece is negative 2. This piece is negative t over the square root of 20 minus t squared. Right? And so we're left with that. And now our job is to, if we had to do this by hand, like you could just plug it into a calculator, right? If we had to do it by hand, which is possible, then we'll have to simplify. So let's bring the 2 pi to the outside. We're going to integrate from 0 to 4. Nothing you can do about this right now. We're going to clean up the inside. Negative 2 squared is 4. If you square this thing, you're going to get t squared over 20 minus t squared, right? When you square the square root, you just get, they cancel out. And if we, what do we got to do here? We have to find a common denominator so we can actually combine these two together on the inside of this radical. So we're going to multiply this 4 times 20 minus t squared on the top and the bottom. Right, what that's going to give us is 80 minus 4t squared, and there's this t squared over here, all over 20 minus t squared, and then the outside piece is still here as well, right? There's still 2 pi 0 to 4 square root of 20 minus t squared. And let's keep cleaning it up. If we do this, it's going to be 80 minus 3t squared, right? We're just combining the negative 4t squared with the t squared, all over 20 minus t squared. Which then, if you remember your properties of when you're multiplying radicals, right? Or maybe something simpler than multiplying radicals is if you have a radical of a fraction, you can always take the radical of the top and the radical of the bottom separately. And in this case, when you do that, you can notice that the denominator here is going to cancel with that one. And so all we're going to be left with is 2 pi square root from 0 to 4, or sorry, the integral from 0 to 4 of 80 minus 3t squared. Which is, so I guess now we're going to put this in our calculator after all that work. It's because there's not really any way to integrate that piece as it is, but at least it's a lot simpler to put on our calculator now. Square root of 80 minus 3t squared. And so we're going to get 2 pi times 31.7768, which turns out to be about 199.65 6595. Right, so that would be the area. Sorry, not the area, this would be the volume, right? So like units cubed of the surface when you rotate it around the x-axis. Maybe it'd be interesting to kind of look at what that surface looks like so we can see what we're rotating about the x-axis, right? So let's go and just graph these real quick. 3 minus 2t, and then here we're going to do square root of 20 minus t squared, and if we graph it, we're going to need to zoom out. So it's basically taking that region, rotating it around the x-axis, and we just found the volume of that.